My video about this craptacular little CNC machine has over 1 million views on it, which is like mind-blowing to me, and it's so awesome. Thank you, by the way, to my loyal viewers. You guys are awesome. Anyway, that video is a little long in the tooth, and it's time to update it. So the first thing that we need to talk about as far as updates go is the software. The software that generates the tool paths for actually, telling the machine where to move to cut out your part. And the software that I showed in that video was called ArtCam, which was an Autodesk product, and Autodesk, the publishers of Fusion 360 and AutoCAD. Autodesk has this really robust history of buying up programs from smaller developers and offering them for free, giving them away for free before just killing them dead. You can't get them anymore, or before making them something that's expensive and you have to pay for it. So ArtCam is no longer available, which kind of sucks, but the original publishers apparently were able to hang on to their code base and their intellectual property, and they are reselling ArtCam under the name Carveco. And they do not advertise this because I think that's probably in the contract they can't say the formerly called ArtCam, but it's definitely formerly called ArtCam. Carveco is ArtCam. So yeah, everything that you learned about ArtCam in that last video, go buy Carveco and you'll be able to use that knowledge. And Carveco certainly seems like one of the best options out there for the DIYer in CNC machines. So it's worth it. It's worth it to look into. But I think there's a free version. There's a free workflow that we can come up with to do some good cuts here on one of these machine like this size. So that's something that I'm going to teach you in this video, is just how to do pretty much anything well, not anything, but do some very high level toolpath generating for free. So that's thing one. And the second thing to talk about, to update from that original video, is the machine itself. This one is terrible. You don't want this. The only realistic thing you can do with this machine is cut out some circuit boards, some PCBs, which now that we have JLB PCB, or I don't know, what is it, Osh Park or whatever. We have all these companies where you can get professional circuit boards. You shouldn't be cutting your own circuit boards. It's really a waste of time. So we want a real robust machine, and this one here in the background is that. This is the Fox Alien 4040-XE. And I did the live unboxing and assembly of this CNC machine today, and I'm super impressed. I think this is the sweet spot. I think this is about the size and about the money that everybody should be spending on a CNC machine if you don't want to be frustrated and you really want to do some good work. But it's a $1,000 machine, which I know is way out of most people's budgets, and I know what you guys want. You want a machine that's like this size. You want to spend like less than $200 or at least less than $500 on it, and you want it to be able to cut aluminum. So you can make, I don't know, brackets for your motorcycle, or little mechanical parts for a pew-pew, or stuff like this. So I get it. I know what the goal is, and I think I've got an option for you guys. So that's what this video is going to be all about. We're going to find a machine that's basically the updated version of this, and we're going to learn how to use it. So let's see what we've got here. Yeah, so looking at these plates, I mean, just look at how thick that is. It's all metal, it's all aluminum. These bearings here go everywhere, so no bushings anymore that are gonna wiggle on us. This looks really promising. I think we'll be able to get a good router out of this. Alright, I've got the machine fully assembled, and it is a sexy beast. I am loving this thing, you guys. So let me talk about some of the fantastic features. First of all, I love the red anodized colors on all of the plates. Awesome. The lead screws are integrated into the stepper motor, so that's glued into the armature inside the motor there. So that's just a very nice connection that doesn't require either a rigid connection or a flexible connection, as we typically see with stepper motors on like 3D printers. There's actually a retaining bearing, and then this metal knob for adjusting the axis. So very high quality feel to the components there. It's a really well designed, simple, but just really well designed kit. So yeah, I am very impressed with this machine for the price that I paid for it. But I do have a couple of small criticisms. They're pretty minor. The first one is this flux ring. Now this goes around the motor here, and it contains the invisible magnetic flux into the motor a little bit better, which increases the efficiency of this motor by about 5%. So it's a small increase, but it's worth it. And as it comes from the factory, that does not fit in between the plates. So you've got to trim that flux ring down so that it will fit in between those two plates. Now the next problem I have is a little bit more serious. It involves the anti-backlash nut on the lead screw. So if this was a more expensive CNC machine, we would see a ball screw here instead of just a regular old lead screw. And ball screws have lower lash, or also called backlash, but lash is just the term there. And so yeah, the anti-backlash nut does help, but if you don't install the anti-backlash nut correctly, this problem happens with the bed, where you get a bit of play in the bed. Now that bed is moving the thickness of a piece of paper, and that's pretty substantial, and it's going to manifest in your final geometry when you're cutting things. So we definitely want to fix that, and here's how you do that. This is the spring that comes with the anti-backlash nut, and we need to shorten it so that it can work correctly. So take a look at this picture where I'm holding the spring compressed next to the anti-backlash nut fully installed. So you need to match that gap there underneath the shoulder of the nut. In this case, I need 5.5 turns. There we go. See how tight that is? We should have no more problems, at least not the normal operating forces of this small machine. Okay, so I think I've got this thing tuned up as good as it's going to get in its stock configuration. So let's talk about just what makes this machine so much better than all the other comparable machines. Like literally, I wouldn't buy anything that's less expensive than this. There's a whole lot of $200 options, but they're junk. Let's talk about the stiffness of this machine versus this machine here, shall we? So, these are pretty similar sized machines. I do think the bed on this one is just slightly smaller than this one, which is already starting to have an advantage as far as stiffness goes. And so this little stick here is going to be a demonstration. If I hold this right here, so effectively that's the length of my structural member, and I try to bend it, not happening. But if I go the extra length, totally can bend it. And if I flip this on its side, now this is twice as thick as that, and I apply that same amount of force that you just saw me applying, I can't bend that stick at all. So we have a number of things at play here. First of all, the thickness of the member, also the total length of the member. Now, that's key, the length, because look at all these other machines that I'll flash on the screen. These are your, under $500 CNC machines available from China. And as you can see, every one of those machines is larger than these two machines, which means that it's just going to be less stiff based on the length. If you want to keep the same stiffness and increase the cuttable area of the bed, you're going to have to bump up the rigidity of the frame, which means making the frame larger. But most importantly, it means making these linear motion rods thicker in diameter. So even these two machines have a difference in that. So this is 12mm rod and this is 8mm rod. And I looked it up. I hadn't done these equations for about 7 years since I was in school. The moment area of inertia of a cylinder, that's the equation there on the left. So for the 8mm rod, we have 201. And for the 12mm rod, the moment area of inertia is 1018, rounded, of course. So that's huge. 5 times more stiff than this one, just by being 50% larger in diameter. So just an enormous improvement, which should make that critical. It's always the motion system where you get the most flex out of a machine. However, everything about this machine is also beefed up. This is 40 millimeters thick extrusion, whereas this is just 20/20 extrusion, so it's 20 millimeters there. And on the side there, that's a lot thicker than 40. That might be 50 everywhere we're considering. So a pinned connection, well, I'm sorry, a rigid connection. It's not a pinned connection, much more rigid-like than this attachment mechanism here for this machine. So we're already stiffer there, but the problem between these, with this machine here is the 10 millimeter thick plate is still half as thick as the 20 millimeter thick, extrusion there. So theoretically, this machine could do that, could flex in that direction. But not so fast, because what we have here is some more of that 40 millimeter extrusion with 2 bolts holding it, rigidly to the plate, and then of course the 6 bolts there, which means that we have a rigid frame going on here, and that is not a very long distance between those cross members. So contrast that with this, that's a pinned connection for sure. At the top of that very long run, everything about this frame is stiffer than this one. And what we're left with, the Achilles heel of this machine as far as stiffness goes, is this axle going through the motor. And that is a 5 millimeter axle. And behind this, this bit of plate here is the joint between the collet and the axle. And there's that moment where it can bend. And actually the axle can bend in between the bearing up here and the bearing down there, like internally to the motor as well. We'll see what it does once I try to cut with it. Let's take a quick minute to talk about the control board on this little CNC machine. So that is a Chinese clone of an Arduino Nano, as you can see right there. This is the on-off switch, push button on-off switch. There's the power jack. These are 3 Polu A4988 stepper motor drivers, obviously Chinese clones on those. So these are going to be terrible for the micro-stepping. They are not very fine resolution, and also they're very noisy. But we don't really care about that kind of a thing when we're going to be making all kinds of noise cutting through things. So those are going to be the quietest part of the machine. This here is the power, and ground signal that are going to the spindle motor, and this is the MOSFET that hopefully will give us pulse width modulation, so spindle speed control. So all in all, it's a pretty decent little cheap control board, and just like all CNC routers, it's just for some reason it's still the paradigm that you have to keep it connected to your laptop, which is running a dedicated software, a controlling software that's going to be sending the G-code line by line, or maybe in packets of 10 lines or something like that, to the controller here. But if this gets unplugged from your computer mid-job, then the whole job is ruined. Speaking of connecting the CNC machine to the computer, let's make that happen right now. So I will link this webpage here in the description, and this is the universal G-code sender that goes along with Gerbil. Now Gerbil is the software running on the Arduino that controls the machine. So the universal G-code sender, you can get 2 versions of it actually. You can get the classic version, and you can get the more modern version. So if you go to downloads and then download page, you can see that there's the classic version and the platform nightly version. Now I'm going to go with the platform version just because it looks fancier. The classic version I'm sure will work just fine. Okay, and once you've downloaded that, it's a zip file right here. You unzip it and you go into the bin folder, and then you just double click on the on whichever version you want to install. I installed the normal version, not the 64-bit. I don't really think we need 64-bit functionality for this tiny little program, and also I don't have Java installed for 64. And this is what the program looks like when you first open it up. So this welcome page probably full of lots of good information for all of you all, but I'm going to close that out. I'm also going to, I want to see this jog controller here. That's very important to me, so I'm going to put that part right, I don't know, let's put it right there. There we go. So now we can see jog is front and center. This visualizer here is where we're going to watch the job happening once I'm sending a job. Send notes, I don't really think that's all that important. The digital readout is more important to me. This is some pretty fancy stuff. You used to have to pay a bunch of money to get a machine. Well, you used to have to pay a bunch of money to get a machine that did any of this stuff, but the digital readout just tells you you know, what everything's doing, what your X, Y, and Z coordinates are at. So currently it says I'm at 10, 10. I'm not though. I need to reset that. So let's actually reset home right here. So that's the reset 0 in the top left. And that basically just tells the machine that where it's at is the home position. And looking at the machine, we can see that I've positioned it to the lower left corner as far as it will travel, and the bit is just touching this, this material that I'm going to be cutting, the stock material. So I want to call that my 0, 0 coordinate. So here on the software, I can just hit the reset 0 button, and that will declare this position as the 0, 0. Now, on the right in the visualizer, we're noticing that 0, 0 is supposed to be in the center of the bed, or the center of the workpiece. So there's different ways of conceptualizing your workspace, and personally, I like to work in the positive quadrant. So let me show you what I'm talking about. Okay, you remember the grid of points graph from math class in grade school? I hope you do. If you don't remember this, you're going to have a hard time with CNC machining. Okay, so this is your 0, 0 coordinate. It's the place where, you know, things switch over from positive numbers to negative numbers. So in this quadrant, we are at the positive X and positive Y. And I like to work in this quadrant just because intuitively speaking, it's easier for me to understand. Basically, if I see numbers closer to 0, I know that I'm, you know, very much running out of room on my bed. But you also have different quadrants here. This would be negative X and positive Y, and this would be negative, negative, so both negative X and Y, and this would be, of course, positive X and negative Y. Now, some of the DIY programs that we're going to talk about here in a few minutes use the 0, 0 coordinate not as the lower left portion of your stock material, but as the dead center of your workpiece. And I don't like that approach. My brain doesn't like to wrap around that because I'm seeing a whole lot of negative numbers when I'm looking at the digital readout, and it's just hard for me to orient in space. I really like working in the positive quadrant, so that standard to me is the standard that everybody should be, you know, going by. But hey, chime in the comments if you have a good reason why the 0, 0 would ever be the center of your workpiece. Anyway, you need to understand this because you need to understand the movement of your machine. If you are at 0 and you start moving along the x-axis, you're going to see numbers that are increasing. So that is a positive movement. So this direction is a positive movement in the x direction. And if you are up here somewhere and you're decreasing, your numbers are getting smaller and smaller, that's a negative movement in the x direction. And of course the same is true for y. That's a positive movement in the y direction, that's a negative movement in the y direction, and in z towards the camera here, that's a positive movement in z, and away from the camera back towards the origin, that's a negative movement in z. So that's how you do that. Anyway, yeah, we now have a fully functional machine. We can jog it in the positive x direction, we can jog it in positive y direction. Notice that the bed moves down because relative to the bed, the bit is moving up through the stock material. One thing to note about the universal G-code sender here is that there is no button to turn the spindle, the motor, you know, with the bit in it, to turn that on and off. There should be a slider because we have pulse width modulation, so we can control the speed of the spindle even, but it's just not here. There's no interface button. So the way to do that is to type M3 space S and then a number. And the number is between 0 and 1,000, where 1,000 is fully on. So we'll just turn this thing fully on right now, and it's going to be kind of loud. Now we'll go M3 space S 100, so we'll turn it on at 10%. M3 space S0. That's how you test to see if your spindle is working, but you don't need to do that very often. Those commands are going to be embedded in the G-code files, which you'll be sending to the machine. Now, if for some reason you didn't have all of this working correctly, like the firmware came installed incorrectly on your machine, you can go here to the Gerbil wiki page. I'll link this as well in the description. And yeah, this S3, or I'm sorry, it's $3 command inverts the axes. So you go to this table right here above the $3 command, and for instance, if you only need to invert the y-axis, you would put $3 equals 2. because see, the y-axis has a yes, so it will invert, and the x-axis and the z-axis will not invert. So $3 equals 2, and you would just plug that in here in the universal G-code sender right here on the bottom where it says command. So pretty easy stuff, just have to follow the documentation. So yeah, now we're ready to move on to creating the cut file, which means we're gonna have to use 2 other bits of software. So let's talk about that for a quick second. So in order to get this machine to be fully functional, we're gonna be daisy chaining several pieces of software together. So starting off with the machine here, which is running just the Gerbil software. So this is the firmware installed on the Arduino. And yeah, it just, all this does is it takes movement commands and actually translates them into motor movements that physically move the machine. So in order to get the movement commands, which this thing doesn't generate, what we're going to do is we're going to use another firmware, or software, which we were already using here, and this is the sender. So this is the universal G-code sender, which is also in the Gerbil ecosystem, open source, free software. Now there are, of course, other versions of these firmwares and softwares, and sometimes you have them sort of wrapped up together in a proprietary package, or even wrapped up together in a piece of hardware that just is on the side of a more expensive CNC machine. So in our case, we're just using this open source stuff. So this is the sender sending to the Arduino, which is running Gerbil. Now, next up the stream of programs is going to be the toolpath generating software. And so this basically creates a list of movements. Move X 10, move Y 10, move X negative 10, move Y negative 10, would draw a square, which would cut out a square. And that would be a simple list. You could program that simple G-code list by hand, but we don't want to do that. We want the computer to come up with all of the complicated toolpath lists for us. So this is something we're going to have to come up with. How do we write those toolpaths? And then the other thing is, toolpaths have to reference a pre-existing geometry. So you need to make your shape that you want to cut out in some other program. So the toolpath program is separate from the geometry making CAD program. So this is your CAD. So we go from CAD to toolpaths to universal G-code sender to the Gerbil controller, which moves the motors. And so these two here, these are the big question mark at the moment. And we're going to go over some of your options right now. All right, this is LibreCAD, part of the LibreOffice suite of open source software. And you guys can see that I've drawn up this shape that looks kind of like a dog tag. Now, we don't talk about this a lot here in the 3D printing community because it's just really unuseful for 3D printing. It only makes 2-dimensional shapes. It does quite a good job of that, but we need 3D shapes for 3D printing. So fortunately, 2D shapes is all that you need for doing all of the 2.5D type operations in CNC work. So here you can see I've taken that same dog tag and I'm cutting it out of some MDF. So on the left, we have the tool, which you can edit, the tool path, or the tools that you're using, and then the tool paths are key. Now, this isn't a full-fledged toolpath generation program. It doesn't have a lot of features. And 2 of the ones that I would really like to see would be spiraling into the cut. So instead of just sort of directly plunging down with the bit, you want to spiral in. And the reason for that is that milling bits don't like to behave like drill bits. That's not ideal. And the other functionality that I would love to see for cutting metal especially is something that I'd like to illustrate in Rhino. These 2 cylinders represent 2 of the same bits as they're spinning, and in this instance we're pushing the bit straight through the material, just augering straight through, and 100% of the diameter of that bit is engaged cutting through that material. So that puts a lot of stress on the bit, makes you likely to break the bit, also makes it hard for the bit to clear out the chips, which means you're going to be generating more heat, which dulls your bit up more quickly. So this is just a bad way to do it, to just be pushing through material at 100% the width of your bit. A better way to do it is something like this. Now there's many toolpaths, but basically you have that bit and you sort of cut a larger channel with it by going back and forth with the bit like that. And then, you just progressively work your way down that cut. And doing it like this, you could be as little as 25% engagement with that milling bit, which is going to save the life of the bit, make you less likely to break it, and actually make cleaner cuts. So this is definitely an advantageous way to do things, and it's not an option in Carbide Create. Now, the other workflow that I mentioned is this one here, where you start in Blender and you come up with a 3-dimensional shape. And so I can export this as an STL file and then bring it into Mechsoft Visual CAD. And then over here on the left, I can use this workflow to go through the steps to make, just like I said, a single toolpath type, but that is a 3D surfacing toolpath. So look up here, we can see my depth of cut is like 1 millimeter. So for that first bit up there, the whole depth of cut is right on the surface. So you can see those lines. That's the tip of the tool. It's following those lines on the surface. And then out here in space, you can see the lines are just sort of floating there. So that would be a flat bottom. But it keeps working down, flat bottom, flat bottom, flat bottom, flat bottom, till like after what, 1, 2, 3, 4, 5, 6, 7th pass, it will get to that final depth cut right on the surface, and you will have a nice undulating surface cut into your stock material. Let me show you guys what a true toolpath generating CNC program is supposed to look like. But yeah, this is the runtime environment for Rhino. I can do all the normal Rhino stuff. Let's draw a box just because we can. Yep, great. And you can see I've got a couple of lines here. These are just for my reference. That is the travel limits of the machine, and that is the size of the bed. So within those 2 rectangles, you can see I've drawn in this box, and that is meant to be my first test cut. So I'm cutting it out of this stock. That's what those lines are, to represent the stock material, just the chunk of aluminum that I'm going to be cutting this out of. So let me show you guys some of the options available in a real toolpath generating program. Starting with the tool, you can declare all the variables for the tool and the holder so that you can model it so you get clearance so you don't collide with your stock. You can declare feeds and speeds. This is very important. Clearance plane, that's how high up it's going to lift up and over your part, over your stock, so you don't have any collisions. You've got your tolerances that you can set. That comes in handy once in a while. This is also really, really important. You have cut direction. It's called climb cutting or conventional cutting. You can look that up on the internet. It's all over the place, but to be able to switch between those two, there are times when you need to use them. Or hey, you can use both if you want to cut really fast. So then you have your cut levels. This is your depth cuts, but you have really fine control over that, and you have a finishing pass there. You have your entry and exit. So when you want to spiral in and spiral out to get good, plunging is hard with a bit. With a flat bit that, maybe some of these end mills don't even have the center cutting ability, so you cannot plunge. You have to spiral in, spiral out, and the free software only allows you to plunge cut, just like a drill bit, right? So this is also a really good one here. This is tabs. So basically you're just gonna leave a little bit of material there at the bottom to sort of hold it in place. And so if I click the generate button there, it will generate the tool paths. So we can take a look at those. And you see this bump up there, that is where the tabs are happening at. So if we select the whole job and then come to simulate, we suddenly see our stock, and we can press play and watch the bit cut through our stock. And this is just fantastic to have this ability. It's a great troubleshooter. You never quite can predict everything, how it's going to work when you're going through all the settings. So to be able to see your job running before it actually runs, it's invaluable. I can't imagine really actually doing CNC work without this functionality. There you have it. That's what separates the men from the boys, as the saying goes, and the free software just really isn't up to snuff, not even close. So this is looking good. Let's cut it for real. This sounds horrible. Listen to this. I mean, it is working, but it sure doesn't sound very good. And we can see how the bit sort of leads in, and then it's just trying to find a groove. It's trying to move, but it's bouncing all around. And that's why these walls are just so ugly. Those are just so chowdery and terrible.
Now this was a previous cut that I did with twice the feed rate and twice the depth of cut. And look at the size of that circle. Keep in mind that that circle was made with this bit. So look at how much flex that bit is having before it finds its home and starts to carve down the wall. And even then, it's bouncing back and forth across that channel. So just so much movement from this bit and this machine. Now I think I've got a solution. I've got this other ER11 collet, and it's got the wider, can handle the wider shank size. So you see the shank size difference there. It's twice as wide, and we know that twice as wide equals like 5 times the stiffness. So yeah, same size cutter, more or less. Actually, this is an 1/8 inch, so that's 3.2 millimeters, and this is an actual 3 millimeter cutting head. The problem with this one is that it's got 4 flutes. It really changes up the behavior of the cut to have 4 flutes. So I'm hoping that this is going to work. I'm going to try to stay away from 4 fluted bits on this machine from here on out. But this is the only bit that I have that's not, long and skinny like this one.
Look at that bit, just bouncing around in there. Absolutely terrible. I stopped the cut. I've seen enough.
See how much movement there is? That's all flex in the shaft inside this motor. And it might be play inside the bearings of the motor as well.
So clearly we have to replace the motor on this machine. And this is that new motor. This is a 500 watt spindle that comes with its own power supply. You control it with this potentiometer. It can get up to 12,000 RPMs at the highest. Now that's a whole lot better than the stock machine, which tops out at 8,000 RPM. So it's a half again better. There's this flywheel on the end here. So that should smooth the cutout. This kind of keeps the momentum of the spin going. So that's a nice little feature there. Yeah, so this thing came with this mounting solution. Now that's meant to slide on there, and then the 4 bolts go through there, and it also clamps the motor while the 4 bolts go through. But you can see the problem. There's no way to mount this to that machine. It won't go. So clearly we're going to need to modify that machine. But the problem is I have no way to CNC cut metal because that machine doesn't cut metal as it currently stands. I need to mount this motor to that machine to cut the mounts for this motor for that machine. So I'm in a bit of a catch-22 here. Thankfully, I have a 3D printer.
Quick time out before we talk about the 3D printed parts. I just want to talk about price here on eBay. I can find this printer as of, the 23rd of November 2020 for $290, and that 500 watt spindle with the controller for $86, so under $400 for both of these. And this is the geometry that I've come up with. This bit here will hold the motor. You can see this large circular portion here holds the motor, and then the smaller circular punch outs hold the linear motion bearings as well as the T-nut for the lead screw. And here it is, fully printed up and installed on the machine. The tolerance was tight enough that it was actually a press fit to get these bearing blocks into the print. So I didn't need to install the screws. This is only a temporary solution. And being that it's only temporary for me, I printed this out of PLA, which is really not ideal for long term. And the reason is that PLA suffers from really bad creep. Here's an example of that. So this is one of those headphone hooks that was attached to my desk for a couple of months. And when this started off life, that was not as spread open as it is. Those were parallel lines to each other. So PLA just glacially moves over time if it's under pressure. Now all plastics do this, but PLA is way worse than the others. If this was going to be my final solution, what I would have done is make it out of probably carbon fiber impregnated PETG, because PETG suffers from the lowest creep, and I think that carbon fiber additives make it suffer from even less creep. So yeah, this could be a final solution. It really is stiff enough, but in my judgment, it's not good enough. I want to make it out of aluminum, so we'll get there. Now, this is the other bit of geometry that I printed up. It's that lid to the power supply here, and you can see that it accepts the potentiometer as well as this switch, which turns the motor on and off, and then it just sort of tidies up the wiring, so we're not going to be exposed to mains wiring. Now, we have a small problem because this motor apparently maxes out at 12,000 RPMs, so up there. But we probably, most of the feeds and speeds that other people are using on the internet
are down around 10,000 RPMs. So I'd really like to know how fast this motor's going. And there is the trick to that we can do right now. Here on my phone, I've got this frequency generator running. I can just stop it and start it, but it's playing a low note at 167 hertz. And if I put this to the microphone, you can hear what that sounds like. So 167 hertz means 167 times per second. So you multiply that by 60 seconds in a minute, gives you 10,000 waveforms in a minute. So 10,000 waveforms is the noise that this motor is going to make at 10,000 RPMs because the motor's not perfectly balanced. So you can tune your motor just like you would tune a musical instrument, and in that way, without having any other special measuring device, you can figure out how fast your motor is going. Hear the motor, hear the tone, same note. So now that the motor's installed, we're ready to cut some metal, but we want to make sure that we're getting the maximum driving force from the stepper motors on this machine. And to do that, we need to turn up the voltage reference, or the VREF, on these A4988 stepper motor drivers. Now this machine that I have here is quite a few months old, so I don't know what you guys are going to get if you order this today, but mine came with these stepper motor drivers, which on the surface are almost indistinguishable from the ones that I've replaced them with. But for some reason, the voltage ref max on this one was 1.1 volts, and these ones get up to 1.8. We don't want to burn up these stepper motors, but we do want to give them as much juice as they can handle. So let me show you how you get VREF. So you need a digital voltmeter, and then you take your negative lead and you connect it to a ground pin here on the control board. So with the positive lead connected to your screwdriver, you just touch the screwdriver to the potentiometer. That's the little screw adjuster on the control board there. And then you can see I've got this one set too high at the moment, so I'm going to back it down until it gets to, 1.3. And there is kind of a science to this. You can go read about it on the internet, but I just like to do it this trial and error method, and I found that 1.3 volts is making this machine quite powerful enough to do what I want to do so far. Our feed rate is 200 millimeters per minute. I don't know, I'm just going with that speed. Now at slower speeds, this machine will be more powerful, but let's just see how good this does. I have here just a fish scale, not for legal trade, so who knows how accurate this is, but it'll be accurate enough. And then I'll hold this and we'll just see how high we get. 25 pounds? So I was able to get a similar pull factor from the stock control boards at a VREF of about 0.8. So you might want to go with that if you are not going to replace these stepper sticks. Okay, so the machine is adjusted so that it's got a good amount of push through the material. The new spindle is mounted and working fine, and we're able to use the tone generator to figure out how fast this is going. So we should be ready to cut parts now, cut some aluminum maybe, but there's a problem. You see this part right here is a combination flywheel and fan, and it basically blows a small amount of air onto the body of the motor here just to keep it cool. But I have no idea why they did this. This part is wider than the body of the motor, and so the motor, you can see that air gap, that light gap through there. There's a good millimeter of clearance, but this part here is hitting the stepper motor. So I'm going to redesign this part so that we no longer have that collision happening. Basically, the diameter on this is the same size as the motor body, so we won't have that rubbing happening anymore. And I didn't do anything special to this design. It's pretty much the same technique that they used on the stock fan. And that means that the blades here are 2 millimeters at this side, and then on the other side they're 3 millimeters. So that's not very steep angle to those blades, but at 12,000 RPMs, it creates plenty of downdraft across that motor to cool it down. The one thing I kind of changed up is you can see these sort of angled pie-shaped pieces there, and that's just to help with the printability of it. You'll just throw that piece away. That's just sort of like built-in support material. And here's the test cut that I'm really happy with. I think with these feeds and speeds and this bit, I can make this work to finish modifying this machine. So this is pulled straight off the out of the stock material. You can see I left the tabs on there just so that you guys could see it, but they're easy enough to cut off. They're real thin. In fact, I might be able to just bend them off. They might fall off there if I just do that a little bit. But anyway, you can see there's other burrs. You see the other burrs around the cut, so there is some cleanup to do. And the interesting thing here is the fact that that hole right there is smaller than the bit itself. So this was the bit that I used to cut all around the perimeter and do that central hole, just like that. But for the other hole there, I actually used a smaller bit, a 2mm instead of the 3mm bit here. So I was able to do a bit change in the middle of the cut job and get that hole drilled. So that means that I can accomplish everything I want to accomplish as far as cutting out the geometry to finish mounting that motor to the frame more securely than with a 3D printed part. Okay, so this here is a bottle opener, and this is rough, and in fact it moved on me during the cut because the tabs that I was using on this one were not as substantial. They were a little bit more thin, and so they broke off and this part broke loose at the very end. But you can get an idea just how rough it is when I'm doing my roughing passes. I've got a finished version of it here that I kind of cut the burr off, filed it down a little bit. And so basically what you do is you have it on a keychain, you just stick it onto the bottle cap. Okay, so I've broken the edges off of this part. I pretty much just ran my knife along them just to get those burrs taken off. And let's give a measure with the caliper here to see the accuracy. Now, this part was designed to be 10mm and 100mm long. So if we measure it in this direction, we're getting basically 10.2mm. There you go. No matter where I measure it, I get the same, pretty much the same. And here in the length, we're getting 100.1mm. Yeah, that's interesting. So basically that tells me that my machine is calibrated correctly with the steps. It's moving the correct distance, but that play there is all going to be in the bit itself, either flexing out of the way or more likely just in slop in the machine. Using lead screws with those flimsy little springs for the anti-backlash nut. But it gets even more interesting because here in the hole, this is meant to be a 5mm hole, and you can see it's almost perfectly on in the y-axis, and in the x-axis, it's again like 5.2. But the x-axis was the one here that was really quite good as far as accuracy goes in that direction. So it looks like my tolerance on this machine is plus or minus 0.2mm. So that's 2 thicknesses of paper, and that's pretty enormous, but I don't know, what do you expect from a $500 machine? And yeah, I kind of haven't been showing you guys all the tribulations and trials that I've been going through, but like here's a cut where the motor was moving on me, and that's why I had to increase the torque on those stepper motors, because you can see that cut path changed. And once I got the torque on the stepper motors, I sent a job wrong with it zeroed up in the air, so it dived way down into the material. It was cutting all the way through that material in a single pass, which is darn impressive that spindle can cut through 3mm of aluminum in a single pass. But you can see that the stepper motors just couldn't keep up. See that funky path was the stepper motors skipping and just being dragged through the aluminum. The problem that I'm having is chatter. That is the number one problem, as expected from these small machines. That's why I bought this super, stiff, beefy, smaller machine, hoping that I would get no flex in the machine. And I can't feel any movement in these bearings, but somehow in all of that, the bit is still sort of moving around, and I can see it moving around as it's trying to cut through the material. Now it might just be flex in the bit. It really might be just that. But there is a significant amount of vibration happening as the bit is sort of just bouncing back and forth. It's supposed to travel a straight line, and it's instead bouncing back and forth across that straight line. So really bad. That chatter causes the bits to break. Actually, this is the first bit that I've broken, but first it broke the tip off of the cutter, like the business end right there, the most important moment on the whole cutter, just basically chipped off. And that's just because of the vibrations, the chatter in there. And once that was no longer able to cut, the machine was trying to push it through the material that it wasn't cutting, and it just snapped that off. So there's my first 1/8 inch single flute end mill bit that I've broken. All right, let's get back to it and see if we can get a successful cut. I think I'll be able to do it, but this is kind of like trying to go four-wheel driving in a smart car, you guys. I'm sure it's been done, but it's not ideal.
And so it begins. Wish me luck.
Here on the left, see this bit that looks like the dog's breakfast, as they say? So that's a bunch of aluminum that has friction welded itself to the bit. Now the cutting edge looks okay, but it's not doing a good enough job clearing the chips out of the slot, and so there's just a bunch of loose chips in there that have, mashed themselves and bonded with that bit. So this on the right is what one of these bits is supposed to look like. This bit will never be the same. Obviously, carbide is a whole lot harder than the aluminum, so I can chip off the majority of the aluminum that you're seeing here, and it will work okay for a little while, but it's never going to perform as good as a new bit would perform, and it won't be too long until this buildup happens again. And the reason for that is that the surface of the carbide has microscopic pores, which have now been filled up with chunks of aluminum. And so, basically there's an aluminum coating on this carbide at this point. So the reason you use single fluted bits is to try to avoid this kind of a thing. Single fluted bits are the best at clearing out all of the debris, all of the chips. But without running coolant of some sort, you're always going to have chips in those channels. So this is why all CNC machines, at least the good ones, all run coolant. And yeah, it's kind of a conundrum. This is far from ideal. And the problem is that while I haven't broken a bit and the geometry seems to be cutting acceptably, the chatter, oh my God, it was so bad. And it's warbled out that hole, or that slot, quite badly to where there's a lot of play. Like this bit should fit in there with no play. It should not wiggle side to side, and there's a lot of wiggling there. Let's have a quick discussion about flute count and RPMs. So this is a single fluted end mill. This is a double fluted end mill. Of course, they go 3, 4, even 5 flutes, although 4 is the highest that I've ever actually used. So the lower the flutes, the lower the flute number, the better it is at clearing chips, but the worse it is at being strong. It breaks. So the 2 fluted bit here is going to be stronger than the single fluted bit, and it's true of 4 fluted bits. They're even stronger still, although there is a diminishing return there. But the point here is that a single fluted bit has only a single cutting edge. So with each revolution, you only get 1 cut. A double fluted bit gets 2 cuts for every revolution. So there's a sweet spot in metal. There's an optimal speed of, it's called inches per minute or whatever. You want the cut to happen with the feed. There's a balance there. You can't just sort of force it through. So the optimal speed to cut a single fluted bit is going to be, well, half as fast as a double fluted bit. So there's an interplay there that's very important, and you need to look up feeds and speeds on a table, or you need to get a program to tell you the optimal feeds and speeds. It's basically the core of successfully cutting metal, is getting your feeds and speeds absolutely perfect. And you can trial and error it yourself if you want to do that, but it's best just to go to where the experts have compiled their knowledge, and there's a science to it, and you don't have to figure this out for yourself, but you do have to pay somebody, generally speaking, to access the database where all the different combinations are accounted for. Okay, so you guys saw the single fluted bit all clogged up with aluminum. And this is my 2 fluted bit that we started off the video with. And I've chipped it clean the best that I can, but there's still aluminum coating the flutes here. So I can soak this in a bath of lye or some other kind of chemical similar to that and clean off the aluminum. But that's kind of a pain in the butt, and it's just going to get clogged up again really quick. And in order to avoid clogging up your flutes with aluminum, you need to clear the shavings more quickly. And in order to do that, I was using just a spray nozzle like this. So I was just following the cut
by hand, babysitting the cut and just constantly spraying on it, and that worked. My bits were no longer getting clogged up with aluminum. So in order to not have to do it manually, I've rigged up this other air nozzle from my air compressor. And you can see I've just got some 3D prints holding it in place and keeping a constant stream of air blowing on it. And this is doing the job nicely, keeping those chips away from the cutter so that the cutter doesn't get all jammed up. But the problem with the cutter, you can see, is it's flinging, shards of aluminum all over the place inside of this box. That's why I'm now doing the cut job inside of this Tupperware. And the shards of aluminum blowing onto the electronics short out the electronics. They literally, bridge the gap between positive and negative connections. So I've made this board here where I've got my control board, PCB, covered with a couple of cooling fans, and I've got the controller for the motor right there, and I hang that off to the outside behind where the air blows. So the air is blowing kind of forward, and some shards of aluminum definitely still make it up and over and kind of get on top of the covers here, but for the most part this seems to be working here. So if you want successful cuts using a machine such as this, you will need to do something similar to this. There's just no way around it.
It's time for a reality check on this CNC machine. So I've been working on this for about, almost 2 years now, and off and on, but I've been wanting to do this project, and I really just wanted this to be my best video ever. And the saying goes, the perfect is the enemy of the good, and the punchline, this part right here, of this video was supposed to be me using the parts that I had cut with the machine itself to upgrade the machine so that I now have metal brackets holding this more powerful motor in place. But it's not going to happen. And it's not going to happen for a couple of reasons. First of all, even that professional level toolpath generator that I'm using, which is RhinoCam, amazing, fantastic program. If you use Rhino, definitely get that. It's worth the money. But this adaptive toolpath that does the sweeping action that I was talking about, I really need that. I need that toolpath to compensate for the lack of rigidity and stiffness in this machine. I just don't have the oomph. I have the strength. I don't have the stiffness to push through with that entire face of that bit, to push through the metal, even when I'm just doing a very small depth cut. It just doesn't work. I need to be taking smaller bites off. And I think there must be some sort of a patent on that toolpath because it doesn't seem that hard to implement. So I don't understand why none of these consumer level toolpath generating programs give us that functionality, because it's really needed. It's really needed. And the other reason I'm throwing in the towel is because fundamentally, I don't think I'll ever get this machine to work. Okay, so even if I replace those brackets with metal, and there's absolutely zero flex between the bearing blocks and the motor here because it's in metal, I still have bearing blocks on shafts, on 12mm shafts. Well, those aren't perfect. It's not an interference fit. They slide, so there's a slight wiggle. Now, I didn't measure it. Maybe it's only a 1/1000th of an inch wiggle, but that 1/1000th of an inch this is cantilevered out there. That's cantilevered a good 4 inches out there. So we have some seriously cantilevered forces out there. So 1/1000th of an inch here could equate to 5/1000ths of an inch out there, and 5/1000ths of an inch is significant when it comes to chatter. It's going to break bits, and I've broken at least 10 bits trying to get this part to be made. I finally thought I had it with the air spraying on it. That was a massive improvement, but I still broke bits. When I went to get really deep, I was still breaking bits. So yeah, this is a no-go, and I can't recommend this machine to anyone because of that. I mean, there's more problems with the machine. You can see the exposed rods down below. So all of my chips are ending up on the lead screw and the rods down below. So I'd need to put some sort of a bellows or some sort of a cover to try to keep the chips off of those mechanical components. So all in all, I quit. I quit. This type of machine that looks like this, that basically looks like a 3D printer, is a bad idea for CNC machines. So with that in mind, I'm moving on we're gonna move up to the $1,000 machine. There are videos of similar machines that, well, let's be honest, this is kind of a copy of the more similar machines to this. So this is not they're not the pioneer of this form factor. And the pioneers of this form factor are cutting metal way more successfully than I'm cutting it there. And part of the reason is that is, well, that's about the same cantilever, but that's a whole lot more beefy of a mechanism, all metal everywhere, and a nice, strong, powerful motor. So I'm hopeful that I can cut aluminum more successfully on this machine than I'm doing it on that stupid little machine. So that's the end of it. Look forward to this review and to putting this CNC machine through its paces, and I quit on the 1310, and you should not buy it either. So yeah, that's where this video stands. Big, huge shout out and thank you to these guys. These are my executive producers, and these are my Patreon supporters. Without you guys, I would not be making videos. So thank you so much, and see you next time. Bye.